Hello, the topic for this video, force components and resultants, is one of absolutely critical importance to success not only in CE 300, but in all of your subsequent engineering courses. Consider, for example, the force 1 and force 2 that you see depicted on the screen. If the question is, what is the resultant of these two forces, you have a couple of options. Option 1 would be to simply use the vector addition that you're probably familiar with from previous math courses, where we take each vector and apply the parallel vector from the head of the other vector, and then simply from the tails of the two vectors to the point where those two parallel vectors meet is in fact our resultant vector. Now I should note that all of these forces are vectors, so we'll note that with just a small arrow on the top of the letter. That's one way. However, that's not the most practical way in many engineering applications. In many applications, we need to look at components of a force. Now, in order to talk about components of a force, we need a coordinate axis system. So let's define a coordinate axis system similar to what you've probably seen before. X and Y orthogonal components, or correction, orthogonal axes, where they are at a 90-degree angle to each other. In order to calculate the resultant, we first must find the component of each individual force. So let's first look at force 2. If we sketch force 2 along with a coordinate axis system that we have defined already, and we need that critical angle alpha, each component is simply the projection of the force onto the various axes. So in this instance, we would have an x component, and we'll call that F2x, and we'll have a y component, we'll call that F2y. Again, these are all vectors, so for completeness, we should have a vector notation on the top. Noticing that we have now an angle and basically a right triangle, we can make use of our old friend SOHCAHTOA to determine which trigonometric function we need to use. So if we take a look, we'll first look at finding the x component, and so we need to find the relationship between the x component, or the adjacent side, to the force itself, F2, which is be the hypotenuse. So we're going to compare the adjacent to the hypotenuse, so we're going to make use of the cosine term. So we can rewrite this as the cosine of alpha is the adjacent side divided by the hypotenuse. In this example, that is F2 sub x divided by F2. Rearranging terms to solve for that force in the x direction, we see that it is equal to the magnitude of the original force times the cosine of that angle, alpha. Similarly, the y component would then be the magnitude of the original force times the sine of alpha. Now you might ask, what if we had been given this angle? We'll call it beta. The same logical progression needs to be done, and in this case we would look for the opposite side compared to the hypotenuse, or the opposite side compared to the hypotenuse. So we would need to make use of the sine term. So we could say the sine of beta is equal to the opposite divided by the hypotenuse. In terms of this force, that's F2x divided by F2, or in other words, the force in the x direction would be equal to the magnitude of the original force times the sine of that angle beta, and we could continue that along with the y component of the force being the magnitude of the original force times the cosine of beta. Now, regardless of which way you choose, looking at angle alpha or angle beta, you're going to end up with the same numerical result. Let's now look at force F1. F1 has been given to us slightly differently. We don't have an angle. Instead, we have slope information. We know it has a rise of a for every run of b. Now, using Pythagorean theorem, you can compute c. Just recall that c is equal to the square root of a squared plus b squared. Knowing that, and again, remembering that we are in this coordinate axis system of x and y, same idea, we need to look at the projection of each onto each axis. So we'll have the x component of force 1 and the y component of force 1. Now we can make use of our understanding of similar triangles. Knowing that we have a triangle that has sides A, B, and C, and this is a right triangle, and we also have a triangle of forces that are composed of the original force F1, the y component of that force, and the x component of that force. Using the idea of similar triangles, we can relate the x component to the original. So we can relate the x component to the original force is as B is to C. Rearranging terms to solve for that x component, we'll come up with the result that the force in the x direction is equal to the magnitude of the original force times the ratio of side B to side C of our slope triangle. Using the same idea relating the y component to the hypotenuse, we'll use the ratio of A to C, so we see that the y component of our force will be the magnitude of the original force times the ratio of side A to side C. Now the question is, how do we take these components of these two individual forces, combine them together, and find the final resultant of the two forces together? It all begins with simply adding the components together. So we will say that the resultant in the x direction is equal to the sum of the x components of the individual forces. In this example, we have two forces. We have, therefore, two terms in this summation. If you have three forces, you'll have three terms in that summation, etc. Again, for completeness' sake, these are all vectors. We'll do the same thing for the y component by summing the different terms, or the various y components from the various forces. We'll find the y component for the resultant, which we can then use with the x component of the resultant. Now, if we just graphically add these together, we'll see that our x component is going to come out at about, our y component is going to be about this length, and our x component will be about this length. Now graphically, we can see that if these are our two components, then the resulting vector will be this. That is our resultant force. Question is now, how do we find the magnitude of that resultant force? And the answer is using Pythagorean theorem once again, where we have the magnitude of the x direction force squared and the magnitude of the y direction force squared. We take the square root of the sum of those two squares. That will give us the resultant magnitude. Now the next question is, what about this angle theta? Well, this angle theta can be found by understanding, again, our understanding of SOHCAHTOA. And knowing that we want to relate the, in this case, let's use the opposite side to the adjacent side. So we are going to want to make use of the opposite and the adjacent, make use of the tangent term. So the tangent of theta is going to be equal to the opposite over the adjacent, or in terms of our forces, that will be the y component of the resultant force divided by the x component of the resultant force. Therefore, theta will be equal to the inverse tangent of the y component divided by the x component. Now, must you always use tangent? Absolutely not. You can make use of either the cosine or the sine. In that case, you would be making use of the magnitude of the resultant itself and one of the two components of the force. So there are many different ways to come to these various answers. Either way is correct, as long as you are using the proper trigonometric terms and the right values for the components of the force involved in those terms.